Well, hello, students. It's Mr. Rich. It is Sunday night, 8 o'clock. It's time for another Mr. Rich Math Q&A. I've got quite a few questions that have come in from students, some specific questions, and also just some general questions of some topics that students that I have tutored want me to go over tonight. So I'm going to be starting with AP Pre-Calc, and we're going to be doing some problems that are related to 2.6 to 2.8, which I know a lot of my students are going to be tested on this week. Has to do with inverse functions, compositions of functions, and I think we're going to focus mostly on inverse functions today and some of the tricky questions that you might see on your tests or your summatives this week. Last week we took the week off. I was out of town, so we did not All right, I think I'm back. I'm not sure what happened there. All right, here we go. So what I'm you should see my screen now. And what I'm gonna do is we're gonna start by taking a look at inverse functions. And let's see if we can maximize that a little bit there. Christina, can you get that thing? Let's see, there we go. I think that's better. Yes, great, awesome, thank you. Well, what I want to do first, students, is just talk about inverse functions, how to find inverse functions. This is something that you did learn about back in Algebra 2 for sure. And let's take a look at a quadratic function. And our job here is to find the inverse of each one of these functions, and then find the domain and the range of the inverse function. Now, since this is, I want to start with a quadratic. So that wasn't the one that I wanted to start with yet. So I want to start over here at 3. Now this right here is a quadratic function. So you should know what the graph of this looks like, given that it's a quadratic and it's in vertex form. So this right here shows that the vertex is going to be at -1, -2. So if we were just considering just a quick sketch of what this graph would look like, we know that at -1, -2 is going to be the vertex, and it does have a positive leading coefficient. So this thing is going to be opening up in that fashion right there. And therefore, we know that the domain of this function is all real numbers, but the range is from -2 to infinity. But notice that they have restricted the domain to be only values greater than or equal to -1. So what they're saying is that we're going to go ahead and cut off this part of the function and only use the right side of the vertex as the function. Now, why would we do that? Because if we're going to do an inverse function, we want it to be a one-to-one function so that we only have one output for each input on the inverse function. So therefore, we can say that for this original function, the domain is from -1 to infinity. That is the domain. But the range is going to be from -2 to infinity. So let's go ahead and write that down. For our function f, they're telling us to restrict the domain to be -1 to infinity. And we know that the range is going to be from -2 up to infinity. So those are our acceptable y values right there. Then what we are going to do is we're going to find the inverse function by switching out the x and y values. So this f of x is a y, so that'll become an x. And this will become y plus 1 squared minus 2. So when we're finding an inverse function, we're going to switch the variables, and then we're going to solve back for y. So it's going to take about 3 algebra steps is all. I'm going to add the 2 over to the left side. That'll give me y plus 1 squared. And then we're going to square root both sides to get rid of that square. So we now have the square root of x plus 2 is equal to y plus 1. Lastly, we can subtract the 1 over here, and then that's going to become the inverse function right here. So this is the inverse function of this function. And we now can just simply list the domain and range by flipping the domain and range of the original function, because the domain of f of x is going to become the range of its inverse. So we know that this range is going to be -2 to infinity, and that the range would have to be -1. Sorry, the domain, I had that backwards. This domain becomes the range down here, right? So this will be -1 to infinity. But then the range of this f of x is going to become the domain of its inverse. So this then becomes -2 to infinity. Now, you do have to be ready on your summative for a question that requires you to determine what limitation you must make to the domain of your original function, maintaining the range without changing the range of the function, but ensuring that its inverse will be a function that passes the vertical line test. So you would have to know, perhaps on a problem, that you needed to restrict your domain to greater than or equal to -1 or less than or equal to -1. Okay. And so that's going to be our final answer there. And we've got the proper domain and range listed here. Now, the other thing that I wanted to go over for the AP Pre-Calc students was what this is going to look like when you have to find an inverse function for a rational function. And we'll start off with this problem here, number 6. So our job is much the same as it was previously, is we're going to find the inverse function here, and we want to know what's going to be the domain and range. Now let's consider what the domain and range is for this function. So the domain of this function is going to be all real numbers except for the number 1. So if you go back to rational functions, which we did study in AP Pre-Calc in Unit 1, we also did quite a bit of this in Algebra 2 in the spring semester, that when we set that denominator equal to 0, it gives us the restrictions that we need to make to the domain, because you can't plug in any values of x that would yield a 0 in the denominator. So anyways, the domain of this function is -infinity to 1 union 1 to infinity. That excludes 1 from the domain. Now, the other thing that we know about this rational function is it does have a horizontal asymptote. That horizontal asymptote is going to be at y equals 0. How do I know that? Because the degree on the bottom is bigger than the degree on the top, right? The degree on the top is x to the 0. It's got a 0 degree on the top, first degree on the bottom. Therefore, whenever you have that situation, your horizontal asymptote will be laying right on the x-axis at y equals 0. That being the case, the range is going to be all real numbers except for 0, because we will not have any y values touching the x-axis. So our range is going to be -infinity to 0 union 0 to infinity. But let's go ahead now and construct our inverse function for f of x. As we did in the previous problem, we're just going to do a variable swap. So the y will become an x, and this x that was down here is going to become a y. And then what we'll do at this point is we'll go ahead and solve for y. So I'm going to multiply both sides by y. So that gives me, or I multiply both sides by y minus 1. So that's going to give me this. I'm going to distribute the x. xy minus x equals 2. And again, we're trying to solve this for y. So I'm going to add the x on both sides, and then I will divide by the x that's in front of the y. So I'm kind of doing 2 algebra steps here at once. So that's going to give me an f inverse, right? My y will become an f inverse function of f. And then I will add that x over, so that becomes x plus 2, but then I would be dividing by the x. Now, what's the domain and range of the inverse function? Well, it's going to be, again, a swap. This domain right here is going to become the range of the inverse. So this is going to be -infinity to 1 union 1 to infinity. The range of my f of x is going to then become the domain of its inverse, which is negative infinity to 0, union 0 to infinity. Now, this should make sense that that is what the domain and range is for this inverse function, and here's why. Notice that there now is there has to be an exclusion to the domain of that inverse function at x equals 0, because 0 will make that denominator 0. So therefore, we are excluding 0, right here. So while we were excluding 0 from the range, we are now excluding 0 from the domain, which makes perfect sense when you see that there's an x down in the denominator. Furthermore, you know that this inverse function, if you were to graph it, it would have a horizontal asymptote at x equals 1, or I should say y equals 1, because you've got the same degree on the top and bottom. And when the degree is the same on this rational function, then you've got a horizontal asymptote at the ratio of their two coefficients. So the two coefficients are 1 and 1, and therefore you have a horizontal asymptote at y equals 1. Therefore, we excluded 1 from the range. Okay, so if you, on these rational functions, if you get the domain and range right on your original function, you are going to get the right domain and range without any restrictions, additional restrictions other than what you had in your original domain and range. The other one that I wanted to show you was a little bit more of a complicated rational function right here, because I now have an x that's in the top and the bottom. And so the algebra is just a little bit more complicated when you do your variable swap to solve for y. But let's go ahead and get the domain and range for this. So the domain is going to be all real numbers except for the value of x that would make that denominator 0. So that's going to be, when you set that equal to 0, it's going to be 4/3. So our domain is negative infinity to 4/3, union with 4/3 to infinity. So that's going to be how we restrict that domain right there, getting rid of 4/3. Now we do have a horizontal asymptote at 2/3 because we have the same degree, top and bottom. Therefore, horizontal asymptote is at the ratio of those coefficients. So the going to be from negative infinity to 2/3. And then we would union that with 2/3 to infinity. All right, now let's go ahead and do the algebra that's involved in solving for the inverse function. So that f of x is going to become an x. Those two x's will be switched into y's. So it's going to look like that right there. Next, what we're going to do is we are going to do what we did on the previous problem. I'm going to go ahead and multiply both sides by 3y minus 4 and move that over to the left side. So you now have x times 3y minus 4 equals 3y plus 5. Excuse me. So next, I'm going to go ahead and distribute the x. So this will give me 3xy minus 4x is equal to 3y plus 5. And remember, when you're trying to find the inverse function, what you're trying to do here after you've done your variable swap is solve for y. I want to get y on one side and x on the other. But I've got two terms that have y in them. I've got this 3xy on the left, the 3y on the right. So my job is to get them on the same side so I could factor them out. So this 3y is going to come over to the left side as a negative 3y. That negative 4x, going to bring it over as a positive 4x. Now you can pull this y out, and you're going to get 3x minus 3 equals 4x plus 5. And then, so then what we're going to do is divide by 3x minus 3. And that will isolate the y, which becomes f inverse of x. And you have 4x plus 5. And you have this as 3x minus 3. All right, now I feel like I wrote down something wrong. I did. Okay, I knew something didn't feel right about that problem up here. I don't ask me why I changed that 2 to a 3. So this is actually, all of these 3's here are 2's. That's 2y plus 5. That means this came over as a negative 2y instead of a 3y. That means this is a 2, going back and fixing all of these like that. And then this ultimately, when I divided by the 3x minus 2, was that right there. And that's going to be the inverse function at that point. And the domain and range are going to come over as the range and domain of the original function. So this domain is going to become the range. Negative infinity to 4/3, union 4/3 to infinity, which again makes sense because can you see on this inverse function, there's a horizontal asymptote at 4/3. And therefore we were restricting the range here and getting rid of 4/3. The domain of my inverse is going to be what my range was for the original f of x. So that's just negative infinity 2/3 and union with 2/3 to infinity. Again, that's consistent with the result that we have here because you can tell that there's going to be a vertical asymptote, right, at 2/3. Right, 2/3 has to be excluded from the domain of that function because of the 3x minus 2. When you set that equal to 0, you will find that x is equal to 2/3. That's what makes that denominator 0. Well, that's the AP pre-calc that I wanted to go over. The next thing that I wanted to do is jump over and do a little bit of algebra 2. I had some students ask me about quadratics. A lot of students have started graphing quadratics, and actually, I think we're going to go into polynomials. I think most of my Algebra 2 students have moved into polynomials, or they're wrapping up quadratics this week. So let me show you what I have here for us. Yeah, and I'm going to start with polynomials that you see right here. And the first thing that I want to talk, I will start with quadratics as a polynomial. Right. So one of the things that we know about quadratic functions, and we'll just use our parent function y equals x squared. Right, y equals x squared does have a vertex at the origin, and then it is going up to the right and up to the left, like that. And then we can transform that and move it left, right, up, and down, give it vertical stretches and so forth. But that is basically what the quadratic looks like. When you take a look at what the cubic function looks like, y equals x to the third, it's going to be going up to the right a little bit faster than the quadratic, but it's also then, though, going to be going down to the left this way. And then I'm going to show you the quartic, right? The fourth degree polynomial, y equals x to the fourth. Now it's going to rise even faster than a quadratic because you can tell if you're raising x to higher powers, it's going to rise faster. It does look a little flatter kind of down here in it, but it is going to be rising faster. So in a sense, it does look like a quadratic, a second degree polynomial, because they're both on both extremes, left and right, they're going up to positive infinity along the y-axis. Now I'm going to go over to Desmos and just maybe compare these three graphs for a second. So let's take a look here at the quadratic, a basic quadratic, and a basic cubic function, third degree polynomial, and a fourth degree, like that. All right, so we'll zoom out, and there you can see, okay, didn't like this because I don't have an equal sign here. There we go. So you can see how I was talking about how it looks a little flatter, but you can see that, and they all pass through 1, 1 right there. But the quartic, the fourth degree polynomial, is definitely rising faster than the cubic or the quadratic. Okay, so that's what they look like. So what I wanted to show you is that the similarity between the second degree polynomial and the fourth degree polynomial is they are both going up to the right, up to the left. Now, if I do put a minus in front of either one of these, or let's put it in front of both, I think by now you know that that's going to reflect the function across the x-axis, and it just means it's going to be opening in the downward direction. I'm going to graph one more. I'm going to graph a sixth degree polynomial. And it should be no surprise, it is going to be going down, but faster. So what I want you to see is that when the degrees are even on a polynomial, and remember, degree is the highest power on the variable x. When the degree is even, the end behaviors, that is when you go all the way out to the right, all the way out to the left, they're going to be going in the same direction, either both up or both down, depending on the sign on the leading coefficient. And even, it doesn't really matter what's the rest of the polynomial is. For example, if I say x squared minus 2x plus 7, and we take a look at that quadratic, no surprise, it's going up to the right, up to the left. If I make the minus, put a minus in front, it's going to change the equation in the graph, but it's the main feature that we see is that it's now opening down because that leading coefficient is negative right there. And yeah, and so that tells us of what we call the end behavior of polynomials. And I'm going to show you kind of the overall thing that we're talking about here. What the first thing that you want to know about graphing polynomials in your Algebra 2 class here is that, and let's get our Desmos back where it is supposed to be here. There we go. That if the degree of your polynomial is even, x to the second, x to the fourth, x to the sixth, and it has a positive leading coefficient, it means that the end behaviors, as you go all the way to the right, the function will be going up, and it would be going up to the right, up to the left. If it's an even degree but has a negative leading coefficient, we saw on Desmos that it would be going down, like this. If the degree is odd, 1, 3, 5, 7, 9, what that means is it will be going up to the right and down to the left if the leading coefficient is positive, or it'll be going up to the left, down to the right if the degree is odd, but the leading coefficient is negative. And just to hammer that home one more time, if we take this and make it a third degree polynomial, and let's change this up, we'll make it x to the second power, like this. And I'm going to change the scale on this by just a tad. Okay, and then you look at this function, you can see that the degree is an odd degree, but there is a negative in front of the leading term that has the highest power. And so therefore it's going up to the left, down to the right on the extremes. And so it's following this trend right here. That is what you're going to be taught if you haven't learned it already. It's called end behavior of your polynomial graph. All right, and that's it. So what we can do then is, oh, and let me show you how you write or communicate and express end behaviors for polynomials. So let's look at a few examples of that. So this right here, let's just talk about the end behavior of this polynomial. Notice that the highest power is a 4, and it has a negative leading coefficient. So whatever the graph looks like, I know on the extremes, on the ends, it's going to be going down to the right and down to the left. So here's how we express that. We say as x goes to infinity, meaning as you go to the right on the graph, the y values are going to go down towards y values of negative infinity. This says as you go to the left, the y values are going to be going also down to negative infinity. All right, let's do one more, and let's do one that is an odd degree. 2x to the third minus 4x squared minus x. We've got an odd degree, and we have a positive leading coefficient. That means I know that it's going to be going up to the right, down to the left. So if I'm going to express the end behaviors, as x goes to infinity, the y values are going up towards y values of positive infinity. This says as I go to the left, those y values are going to be going down towards negative infinity like that. All right. And notice we're not really drawing any conclusions about what's happening inside here, like closer to the y-axis. We're just talking about what's going on when you get far away from the y-axis, way out to the right, way out to the left. All right, now let's talk about how we determine maybe a little bit more clearly what's happening closer to the y-axis. So that's the last thing that I wanted to cover here, and that's finding what we call the roots of your polynomial. And here is what we want to do. What we are going to do here is we're going to take this third degree polynomial. And we don't know what the graph would look like. We do know the end behavior, though, that because it is an odd power, odd degree with a leading coefficient that's positive, we could say for this polynomial that as you go to the right, as x goes to infinity, the y values are going towards infinity, going up. And then we could say as x goes to the left, to the negative infinity, the y values are going down, negative infinity. So the behaviors are going up to the right, down to the left. But then what we're going to do is this. We're going to find out where would this function cross, where would it cross the x-axis? What are the x-intercepts, or what we call the roots of the function? And the way that you do that for any function is you're going to set the y value equal to 0 and then solve it for x. And the way that we're going to solve the polynomial for x is we are going to factor it. Now, this polynomial is pretty easily factorable. As you get a little bit further into this unit on polynomials and the degrees get a little bit higher, they're going to be harder to factor, and you'll have to use some other techniques to accomplish the factoring, one of them being long division, or what we call synthetic division, which is coming down the road here in a couple of weeks once you get into polynomials. But this one's easy to factor because you can notice it does have a greatest common factor between all three terms. That is an x. So we could pull an x out, and this will make it x squared minus 12x plus 35. And then inside the parentheses, you recognize that as a quadratic. And so that quadratic is itself factorable. So we will factor it as we know how to factor quadratics. That means that I have to have an x and an x here. I'm looking for two numbers that multiply to be positive 35, but yet when I add those same two numbers, I get a negative 12. And that answer is a negative 5 and a negative 7. Now that I have successfully factored this third degree trinomial, I can set each of the factors equal to 0, right? What we're using here is called the zero product rule, that if multiple things, two or more things, are multiplied and the answer is equal to 0, it means one of them must be 0. So therefore, this equation will be true if either the first factor, x, is 0, or the second factor is 0, or the third factor is 0. Well, there's one of my solutions. That one, when you solve it, you get x equals 5. And here you get x equals 7. So that's where we know that this function is going to touch the x-axis at 0, 5, and 7. So let's come over here and sketch what we think a very crude sketch would look like of this function. So let's go ahead and put a set of axes on here. And we said it's going to touch the x-axis at 0, out here at 1, 2, 3, 4, at 5, and at 7. Now remember what we said about the end behavior. The end behavior, we said, was going to be up to the right and down to the left. And so therefore, what we know is going to happen is the function is going to come from up here, cross, let's redraw that, make it a little neater here. So it is going to come down here. This is just a very crude sketch. It's going to come, but it's going to cross here at 7, but it's going to have to turn so it could cross at 5, and then it's going to have to make a turn and then come down like this. So I discovered those x-intercepts, and it helps me make a very crude sketch of what the function will look like. And if nothing else, I know when the function is 0, 0, 5, and 7, but I also know between what x values it's going to be positive. So the function is going to be positive here and over here. So to the right of 7, the function will always be positive. In between 0 and 5, the function's values are positive. When is the function going to be negative? It's going to be negative when it's to the left of 0. And when it's over here in between x equals 5 and x equals 7. And then the last thing that we'll do here is we'll just go ahead and graph the function and just confirm that we're not lying, right? That this thing is actually true, that graph is what it's going to look like. And so we're talking about x cubed. Let's move this guy over here. That function was y equals x cubed minus 12x squared plus 35x. And there you go. So you can see we didn't know how high it was going to go or how low it was going to go before it made the turn to get back to the x-axis. But we did figure out where it's positive between 0 and 5, where it's negative between 5 and 7, and of course positive to the right of 7 and negative to the left of 0. Okay, so that was all I was going to cover today. I'm going to check and see if any of my students submitted any questions for us while we were doing this work. And before we sign out, let's do a quick check. Yeah, I do have a few problems. So Olivia sent in some problems here. So let's pull the first one up. Okay, and I think this is coming from AP Pre-Calc. All right, so let's pull this up before we sign off. We did get a question that came in, and let's take a look. That's the question. G of x is equal to 2 to the x minus 5. So this is an exponential function, and we want to know the asymptote, the y-intercept, the domain, and the range. Well, what we know about exponential functions, Olivia, is that y is equal to a times b to the x is kind of our general form for an exponential. So this one, though, has a vertical shift of minus 5. So they took a function 2 to the x and shifted it down by 5. And why is that important to know? Well, because generally an exponential that's written in this form, without that vertical shift, without a plus or minus at the end of it, it does have a horizontal asymptote that's sitting right on top of the x-axis. So because it's got a vertical shift down 5, that means your horizontal asymptote is going to be at y equals negative 5. So it's going to be down here. That's going to be, and I'll call that y equals negative 5. All right. And then the y-intercept. Well, how do we find the y-intercept of any function? Doesn't matter what the function is. If you're looking for a y-intercept, you're sticking 0 in for x. So we're going to find, for the y-intercept, we're going to do g of 0, which would be 2 to the 0 minus 5. 2 to the 0 is 1. 1 minus 5 is a -4. So we know at 0, -4, it will cross the y-axis. Now, the domain and range are going to be simple because for exponential functions, the domain is always going to be -infinity to infinity. No restrictions on the domain of exponential functions. Now, the range is going to be limited because of the fact that there is a horizontal asymptote, and it's going to be on one side of the asymptote. Now, this function is exponential growth because that base is larger than 1. So the function is going to be looking something like this, crossing here at 0, -4. But this would tell me that since the horizontal asymptote is down here at y equals -5, the range starts at -5 and it goes to infinity like that. And that's going to be our range. And it's always a good idea, Olivia, like if you do come up with some answers there, to go ahead and graph the function and see if your answers make sense. And you want to graph using a tool like Desmos. You don't really want to do this on your TI-84 because it just takes too long and it's too cumbersome and it's not worth it. Here's the function that we were just considering. And I'm going to go ahead and graph the line y equals -5 to show that that is what we call a horizontal asymptote, right? If you zoom in on this line, at purple line at y equals -5, you can see that our function is getting, I'm zooming in like crazy here. You can see it's getting close, but not quite touching that purple line. That's a horizontal asymptote at y equals -5. If we come back over to the y-axis, we can click and see that it is crossing at 0, -4. All right. I hope that was helpful, Olivia. I'm going to go and look at the next one. Okay. And it looks like you've got an equation that you're solving, an exponential equation. So let's pull this one up. Here's the equation that Olivia sent in that I think she wants some help with solving. Okay. And if you are watching and you're one of my students and you have questions, send them in now to the email address that you know for me, and we can cover those. If not, this is going to be our last problem of the night. So, Olivia, what you want to do when you're solving an exponential equation is you want to isolate the exponential portion by itself first. So we want to get rid of the -12. So we're going to add 12 to both sides. So we'll have e raised to the 3 minus x. And when I add 12 on both sides, I'm going to make a 26. Now, I will assume that your teacher expects you to give an exact answer, that we're not going to use a calculator to come up with the answer here. So what we're going to do, the way that you get rid of this exponential e, your base of your exponential, because I do need to get rid of it, because how else am I going to isolate the x? What you have to do is use a logarithm. What we're going to do is we're going to take the natural log on both sides. Why a natural log? Because a natural log is log base e. And I want to use a log base that matches the base of the exponential so that they will cancel each other out. So my algebra step at this point is to take the natural log on both sides. So I'm taking the natural log of 26, the natural log of e to the 3 minus x. Well, over here, this natural log or log base e of e, they're canceling each other out. It leaves me 3 minus x. And this is just a number, the natural log of 26. Now, that number is going to be an irrational number. It's going to be a decimal that would repeat, not repeat. And so we're just going to leave it as the natural log of 26. Now, I'll just show you, right? I could tell Desmos, hey, what's the natural log of 26? It's about 3.25809653802 and a bunch more infinite decimals that don't repeat. Now I just need to do like maybe 3 algebra steps to isolate the x variable. I'm going to subtract 3 on both sides. So I have the natural log of 26 minus the number 3. And then I'm going to multiply both sides by a -1. And when I do that, that will give me x equals a negative natural log of 26, and that would become then plus 3. And turning those two terms around, I could call it 3 minus the natural log of 26. And so that right there, Olivia, is your exact answer for x. If you wanted it as a decimal, sure, you could do 3 minus ln of 26, which is a negative 2.58. That, Olivia, is our answer. And students, I don't see any other questions that have come in, so we are going to call it quits here. I hope you all have a great week. I know a lot of my students have Tuesday off for Veterans Day. I hope you have a good time off. Make the most of your time off. And I will see everybody back here next Sunday at 8 o'clock. All right. Take care, everybody. Bye.